This project is a Lambda function-based League of Legends statistics and AI analysis system built with AWS. As shown in the architecture diagram, the front end talks to Amazon API Gateway, and the API Gateway routes requests to several AWS Lambda functions. Those Lambda functions connect to RDS for our application data, and then call the Riot Games API for match history, and finally call LLM services to generate coaching feedback. Okay, our core part of the system is token verification. Similar in Project 3, after a user logs in, the backend creates a token, stores it in the token table, and returns it to the client. For protected APIs like Fetch, Matches, Summary, and Consult, the backend reads the authorization header, looks up the token in the database, and checks whether it is expired, and then uses the matched user information to continue the request. So in simple terms, the token is how our system knows who the current user is. Our main APIs are as follows. Register creates a user and verifies the Riot account. Login authenticates the user and issues a token. Fetch pulls recent matches from Riot and stores them in RDS. Matches returns paginated match history. Summary computes aggregate statistics like win rate, champion usage, and so on. Consult triggers asynchronous AI analysis and returns coaching feedback when it is ready. Overall, this project demonstrates a practical serverless architecture with authentication, external API integration, data aggregation, and AI-generated analysis. The next part will be introducing pagination and the AI analysis system.
Let me introduce the technical core of our display and consult APIs. For the display, we implemented a pagination using a limit and a cursor approach. The front end specifies a limit, for example 10, and the backend will return the latest 10 matches. It will also return a cursor. It is the timestamp of the final record, and the subsequent call will use the cursor, and it will retrieve only records before that cursor's timestamp. This will significantly reduce database search load. Let me demo that. First, we call the matches API, and it will return 5 records and with a next cursor. And the next cursor is the timestamp of the last records. And we can use this cursor to further require five more records. And we can also call this matches again, and it will return no results because the total number of match is 10. For the consult, we adopted an asynchronous architecture. Instead of blocking on an LLM call, this API immediately triggers a separate Lambda B function, which will be responsible for the LLM call. And the Lambda A will return immediately with a processing state, and preventing the timeout. And we also implemented a cost-saving mechanism. If the user has no new match data and a valid analysis already exists, which means the last LLM query time is greater than the last fetch time. And we will return the cached consult result rather than make a call to the LLM API. This will save a lot of tokens. And we can demo that. First, we call the consult. The first time it will call the LLM API, but it will not prepare immediately. It will trigger the Lambda B function, and we can start pulling. And once the consult result is prepared, and the result will return. And the next time we call the consult API again, it will immediately return the cached result rather than make another call to the LLM API.
Hi everyone, I'm Shuran Yan, and I will do the demo for our CS310 final project called Rift Ledger. Rift Ledger is a cloud-based application that helps League of Legends players analyze their gameplay performance and receive AI coaching. Our front end communicates with the backend hosted on AWS. The backend uses API Gateway, AWS Lambda, and Amazon RDS to process requests and store match data. So now, as you can see, this is the login and register page. Let us first register a new account. We have to use a new email here and create a password. Now we have to enter a real game ID. So click the button and it will register. When we click this button, the front end sends a request to the backend API post-register. The backend verifies that the raw account exists using the raw account API before creating a user profile. As you can see, the status is authenticated. It means we registered successfully. And now let's try some fill example. For example, if we do the same email, that email already exists. If we try a brand new email account, still fail, because the ID already exists. So now we have already successfully registered a new account. Let me do the functional demo with a already exists account. First, we have to refresh raw data because there is now 0 matches in dashboard. We do the refresh. We synchronize the player's match history from Royd. The backend calls the Royd match API to retrieve the player's recent match. Okay, we now have 12 match here. The match data is then stored in Amazon ADS so that future queries do not repeatedly call the Royd API. To control database size, the system keeps only the most recent 100 matches per user. This is the match history. The stored match history can be viewed through the matches endpoint. Use API get matches. Each record shows the champion used, the match results, KDA statistics, and other gameplay information. As you can see, showing here, this is the page. The match history endpoint uses cursor-based pagination. Instead of returning all matches at once, the server returns a limited number of records per request. We can click the load more matches to see the rest matches. And we can also do the page size for 5. So only 5 matches a page, and load more, you can see the rest. And to click the page size 20, we can see all the matches. Now let's see the summary part. The system also computes aggregated statistics using the summary endpoint, API get summary. The backend calculates performance metrics such as win rate, champion usage, and average KDA from stored match data. These statistics are computed on the server side rather than the front end. Now it's for the AI consult. It's checking. The most interesting feature is the AI coaching system, which uses the API get consult. The backend sends player statistics and match summaries to a large language model, which generates natural language feedback. This endpoint is implemented using an asynchronous workflow. When the client calls consult, the backend may first return a pending status. A background worker generates the analyze using the LLM. The front end pulls the endpoint until the result is ready. The AI then provides suggestions about the player's playstyle and possible improvements.